My name's Evan Olson, and I'll be solving problem 9.20 of the Fundamentals of Heat and Mass Transfer 8th edition. So for our problem statement, we have a thin-walled container with a hot process fluid at 50 degrees Celsius, which is placed in a quiescent cold water bath at 10 degrees Celsius. And heat transfer at the inner and outer surfaces of the container may be approximated by free convection from a vertical plate. Um, so, as the problem statement said, we have our diagram here. We have a container, thin-walled container, so there's no conduction in the walls, and a adiabatic condition on the bottom. So we can approximate the system as symmetric, and there is uh, this wall can be approximated as a vertical plate. So we need to determine the overall heat transfer coefficient between the hot process fluid and the cold water bath, and we can assume that the properties of the hot process fluid are those of water. So first of all, we have to determine our dimensionless numbers. This is a free convection problem. So we can take all of our fluid properties at our film temperature of our hot process fluid plus our cold process fluid divided by 2. And reason being, we can assume that since this hot process fluid container was just placed in the cold water bath, I'm thinking that this wall temperature is going to be at 50 degrees Celsius, and there's going to be no temperature gradient there since it's a thin-walled container. Um, so we can just take the temperature of the hot process fluid and the cold fluid, divide that by 2, and we get our film temperature, which turns out to be around 30 Celsius. We know our Nusselt number for free convection is going to be in the form of a function determined by the Rayleigh number, which is your Grashof number times your Prandtl number and the Prandtl number itself. And our Grashof number is defined by this equation here. This is our gravitational constant. This is our expansion coefficient. We have our delta t. We have a characteristic length, and we have a kinematic viscosity. Our characteristic length for this problem is going to be the length of the side of the vertical plate, because the fluid is going to heat up and then travel up the surface. And so, knowing that, we can get our water properties at 30 degrees Celsius, our film temperature, which turns out to be all of these. And we can plug those into our Grashof number equation pretty easily, and we get a Grashof number around 1.5 times 10 to the 9. And we can use that to find our Rayleigh number, which is the product of our Grashof number and our Prandtl number, and that turns out to be 8.157 times 10 to the 9. And now we can figure out what Nusselt number correlation we can use. And for free convection, turbulent and laminar flow is determined by your Rayleigh number. And for a Rayleigh number greater than 9, it's assumed to be turbulent flow. And so that assumption, as well as, well, yeah, that assumption gives us a Nusselt number correlation given here by equation 9.26 in the textbook. And if we plug in all of our known values here, we get a Nusselt number averaged over the length of the plate of 290.46. And if we plug that into calculate our convection heat transfer coefficient, we get 896.66 watts per meter squared Kelvin. Part B asks us to generate a plot of the overall heat transfer coefficient as a function of the hot process fluid temperature for the range between 20 and 60 degrees Celsius, with all other conditions remaining the same. So this is pretty easy. You just follow the same exact process to find the individual convection coefficient, except the only thing that would change here is your film temperature, since it depends on your hot process fluid temperature. And so the way you do this is you import a materials property table into MATLAB, or the way I did this was importing a materials property table into MATLAB, and I iteratively calculate the film temperature and evaluate what the fluid property is going to be at that temperature. And then I plug that into the Grashof number correlation and the Rayleigh number correlation to get to be able to plug into our Nusselt number correlation. And I double checked for all of the fluid temperatures. The Rayleigh number is greater than 10 to the 9. And so that makes this turbulent flow Nusselt number correlation valid. Um, and I believe that equation 9.26 is also valid for any Rayleigh number. And there's one that is specifically meant for flows less than 10 to the 9. And so if it did fall below that, this equation would still be valid. But for this case, it's a pretty easy equation to use to just evaluate your Nusselt number at any condition. And so, yeah, if you use that correlation for every single temperature, you get a curve that looks like this. It looks very linear towards the start. It has a higher slope, but then it tails off a bit. And so you get a lower limit at 20 degrees Celsius of 400, around 400 watts per meter squared Kelvin, and at the upper boundary of around 1050 watts per meter squared Kelvin.